Good afternoon, dear students. How are you? I'm fine. Yesterday's class we discussed electron affinity definition and variation of electron affinity in a period. Today's class we are going to discuss about variation of electron affinity in a group. So electron affinity variation in a group, if you move from top to bottom of modern periodic table. So you already know that how many groups you have, totally 18 groups is present in your modern periodic table. And when you move from top to bottom of modern periodic table, electron affinity is generally decreasing. Okay, so why it is decreasing? Electron affinity, why it is decreasing from top to bottom of the modern periodic table? The size of atom is increasing. That means atomic size. Atomic size is increasing. Also increasing shielding effect. Shielding effect is increasing. Due to increasing the atomic size and shielding effect, electron affinity is decreasing from top to bottom of a modern periodic table. So, atomic size and shielding effect, how it is increasing? Because if you move from top to bottom of a group, the elements they have more orbitals than the top of the element. So which the elements which is present in the bottom of the modern periodic table, they have more orbitals than the top of the elements. Because of the size, it is because of the distance from nucleus to the valence electron or the valence shell, the size of the atom is increasing. So when you move from the top to bottom, atomic size is increasing because of the number of orbital is increased, and also shielding effect is increasing. Due to this two reason, electron affinity is decreasing. But we have some exception case. One exception case, in period 16 and 17. Group 16 and 17. Look at this. 16th group oxygen and 17th group fluorine is present. And the next element of 16th group is sulfur, and next element of this 17th group is chlorine. You can see this oxygen, you can compare this oxygen and sulfur. Comparing this oxygen and fluorine with the sulfur and chlorine, their atomic size is less than sulfur and chlorine. So the atomic size is greater here than the oxygen and fluorine, and the electron which is present in the fluorine only in 2s and 2p. So the valence shell is 2p. Here also it is 2s and 2p, but here it is 3s and 3p, 3s, 3p. So the number of orbital it is increasing. Compare with this two elements with the sulfur and chlorine. So the valence orbital is 3p, here it is 2p. So the electrons filling in the valence orbital 2p is compact. It is a compact one than the sulfur, and the electron filling in the 2p orbital of fluorine, it is also a compact system than the chlorine. So this oxygen and fluorine have smaller size, they are smaller size and high electron density. Because of this, oxygen and fluorine have lower electron affinity than sulfur and chlorine. They have lower electron affinity than sulfur and chlorine. But what is the general character of electron affinity in a group? Generally, electron affinity is decreasing from top to bottom, but in the case of oxygen and fluorine, then sulfur and chlorine, it is different. Final periodic trends is electronegativity. It is defined as the relative tendency of an element present in a covalently bonded molecule. So it is a covalent bonded molecules. It is defined as the relative tendency of an element which is present in the covalently bonded molecule so that attract the shared pair of electrons towards itself. So they are attracting a shared pair of electrons, electrons attraction. Covalently bonded molecules is attracting a pair of electrons. So the molecules which is present in covalently bonded, the ability to attract the pair of electron is electronegativity. That is called electronegativity. And electronegativity, it is not a measurable quantity. However, we can calculate this by Pauling's method. And he proposed one equation to calculate the electronegativity is XA minus XB equal to 0.182 root of EAB minus EAA multiplied with EBB power 1 by 2. He fixed here arbitrary value of fluorine and hydrogen 4.0 and hydrogen 2.1. He fixed this value to measuring the other element electronegativity by this formula. XA is electronegativity of element A, XB equal to, it is electronegativity of element B. Both are in covalent bond. We already know that the elements which is present, which is bonded together by a covalent bond, and the effect or the ability of sharing a pair of electrons. That means 2 electrons. So XA is electron negativity of element A, XB is electron negativity of element B, EAB bond dissociation energy. Of A and B. So A element or A atom is bonded with B atom by a covalent bond. So the energy required here to dissociate this bond is known as EAB. That means bond dissociation of energy of A and B, which is in covalent bond. energy EAA equal to bond dissociation energy of A bonded with A. Atom A bond with another atom A. So this covalent bond, we dissociate this covalent bond or breaking this covalent bond with some amount of energy. This is EAA. A. So this bond dissociation energy of A covalent bond A or A single bond A. Then EBB. This is also same like EAA and EAB. So bond dissociation energy of B atom is bonded with B atom. That means B atom is bonded with another B atom with a covalent bond. So the energy required here to break the bond between B and B atoms, okay, in between these two atoms. So electronegativity of a molecule mainly calculated by a nature of the bond. Mainly it is a covalent bond, and the electronegativity values are playing an important role to calculating or predicting the nature of bond. Here we have variation of electronegativity in a period. Totally 7 periods. So how it is differing the electronegativity in a period? Generally, electronegativity is decreasing, it is increasing across the period from left to right. It is increasing. Electronegativity is increasing left to right because of the atomic radius is increasing along the period, and also attraction between the valence electron which is present in the valence shell and the nucleus, the attractive force between the nucleus and electron. So here the tendency of attracting two electrons or a pair of electron is increasing when moved from left to right of modern periodic table. You can see this variation of electronegativity along first period: lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. Atomic number which is plotted in the graph, atomic number and electronegativity against atomic number in x-axis, electronegativity in y-axis. You can see the electronegativity which is increasing. It is increasing. Gradually it is increasing from alkali to halogen. It is increasing in first period. Variation of electronegativity in a group. Generally, electronegativity in a group from top to bottom, it is decreases because of increasing the atomic size and increasing the nuclear attractive force, that means the shielding effect. So because of this, electronegativity is decreasing in a group. So generally noble gas are there no changes in electronegativity. So the electronegativity of noble gases generally they. Take page number 88 and look at the figure 3.7. Here they explain the variation of electronegativity along first group. So what is the first group elements? S block element: alkali metals, lithium, sodium, potassium, rubidium and cesium. So lithium, their atomic size is smaller than the sodium, and potassium is greater than the sodium. Rubidium is greater and cesium is greater than these four. Okay, so now let's see the electronegativity variation in lithium to cesium. It is decreases because of the atomic size is increasing and the shielding effect is also increasing. That means the the attraction between the nuclear and electron, it is increasing. Okay, so here you can see this lithium sodium. Lithium have the value 1. Now it is decreased. Sodium and potassium. Potassium and rubidium have nearly same value of electronegativity. Cesium have less value than these 4 elements. So this is the variation of electronegativity along the first period. So up to here the variation of the periodic trends of physical properties in modern periodic table is completed. Next we will look at the next topic, periodic trends in chemical properties in modern periodic table. Periodic trends in chemical properties of modern periodic table. So the chemical properties like reactivity, valency and electron oxidation state we will discuss in this topic, periodic trends in the chemical properties of modern periodic table. First chemical property is valence or oxidation state. Generally, valency of an atom is a combining capacity which is relative with hydrogen. This is valency, and generally it is equal with the number of oxygen number of electron which is present in the valence shell. So number of electrons, total number of electrons in valence shell, and also it is equal to 8 minus the number of valence electron. So we can use the oxidation number to place the valency. We can use the oxidation number. Generally, this valency is mainly depend upon the number of electron which is present in the valence cell, and the number of electron is present in the cell is same in one group. So the maximum valency is also remaining same in the group. But in the case of period, the number of valence electron is increasing. So the number of valence electron is increasing, so the valency also it is increasing along period. Look at this table 3.16. It is explaining the variation of valency in groups. Take the example group 1 and group 15. Group 1, the name of the group is alkali metals: lithium, sodium, potassium, rubidium, cesium and francium, which is present in first group. So the number of total electrons in the valence shell, it is 1s1, 2s1, 3s1, 4s1, 5s1 and 6s1. So the number of electrons, it is written here, it is always same in the group, it is 1. Okay, so the valency of this first group also it is 1. Okay, so the number of electron is equal with the valency of electron. Number of electron which is present in the valence shell is equal with the valency of electron. And look at the examples 2. Group 15. Elements are nitrogen, phosphorus, arsenic, antimony and bismuth. Number of electrons in valence shell is 5, 5, 5, 5, 5. How it's become 5? In the group it is same, and you can look at this one in 15th group, group number 15, nitrogen, phosphorus, arsenic, antimony, bismuth. Look at this valence electron 2s2 2p3. So the number of electron in valence shell is 2 plus 3 is 5. Okay, so here also it is 2 plus 3 5, 2 plus 3 5, 2 plus 3 5, 2 plus 3 it is 5. So in groups, so the number of electrons in valence shell in a group it will be same. So the valency of that particular group it mentioned here 3 and 5. And look at the variation in periods. The valency in the period, valency variation in the first period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So the number of electrons which is filling in this elements or in the periods of elements it is increased. So count the number of electrons. So how many number of electrons in the valence shell? In the valence shell it is 1, and the beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7 and neon 8. So the combining capacity relative with hydrogen, it's given here 1, 2, 3, 4, 5 and 3 for nitrogen, 6 and 2 for oxygen, 7 and 1 for fluorine, 8 and 0 for neon. Next topic is anomalous properties of second period elements. So the general character of periods in the group also, which is similar, the physical and chemical properties is similar in the same group, but the first element of each group is different from the other element of the same group. For example, here we can take the example lithium and beryllium. Both are in second period, and lithium in first group, beryllium in second group. So you know that first group element lithium, second group element beryllium. Lithium first group element, so this is alkali metals, this is alkaline earth metals. Alkaline earth metals. So the general character of alkali metals and alkaline earth metals are they have the ability to form the ionic compounds. They have more ability to form the ionic compounds. But in the lithium and beryllium, which is present in the alkali and alkaline earth metals, they are involving in the covalent bond compound formation. So they form more covalent compounds than the alkali and alkaline earth metals, because alkaline and alkaline earth metals other than lithium and beryllium are formed only in ionic compounds, but lithium and beryllium form covalent compound. So this is one covalent bonded compounds. So this is one anomalous behavior of this lithium and beryllium in group. So the second period have only two valence orbitals, 2s and 2p. So they have maximum covalence is 4. Okay, so other if you compare this period with the other periods, then they contain more orbitals and their valence shell are showing the higher valencies. So their valence is more and their orbitals also more. One of the most important question from this unit, diagonal relationship. Maybe there's the possibility to ask in 2 mark and 3 mark. So the elements which is diagonally placed in modern periodic table, they have similar properties. This relation is known as diagonal relationship. So the elements are arranged in the diagonal places. They have similar properties. Their character known as diagonal relationship. Look at these elements. You know that this is second period and this is third period. First group, second group, first group, second group, third and fourth. This lithium characters are similar with magnesium. So they are diagonally placed in modern periodic table. And the character of beryllium is similar with the aluminium. It is in the third period. And the character of boron from second period, it is similar with the silica which is present in third period. So these elements are arranged or it is placed in modern periodic table in diagonally. Diagonally it is placed. So the elements which is placed in diagonal place and also the similarities of properties, this character is generally called diagonal relationship. But it is not same for all the elements in the group, but it is same here only the elements which is shown in this figure.